we have 4 speakers, and the first one is Stijn Vansteelandt, coming from Belgium at the University of Ghent. And with no further introduction, let's get started. I think that your display, yeah, show that. Thank you.
Thank you very much for organizing this meeting and for the invitation. I'll maybe start with a disclaimer, which is that I know very little about model selection, and you have to blame Bianca Di Stavola for inviting me, and also Miguel Hernan, because he basically put up a special issue on causal inference that was just published in Statistical Methods in Medical Research. And he decided to invite a couple of people to write on topics relating to causal inference, topics that he thought had received insufficient attention in the literature. And so he asked me to write a bit on model selection and model misspecification. Since I know very little about it, I was quite happy that Gerda Klaaskens, who is a real model selection expert, was quite happy to join me on this endeavor. And so I'll mainly reflect on what, from a causal inference point of view, I think are some of the concerns and issues when building models and also when selecting confounders. So let me give you a little bit of background. As you may know, over the past 2 or 3 decades, there's been a lot of progress in causal inference in thinking how to infer the effect of an exposure A on an outcome Y from both observational data, but also experimental data. And so attention has been given to a lot of issues. There's been a lot of attention looking at complex problems of confounding, such as may easily appear in time-varying settings. There's been a lot of attention being paid to semi-parametric procedures that sort of try to protect, to some extent, against model misspecification bias. And this links a bit to the issue of model selection, and I'll come back to this towards the end of the talk. But most procedures still assume that we, basically prior to starting the analysis of data, even prior to seeing the data, that we know precisely what covariates we need to control for in order to control for confounding, and that also, given the covariates that we have available, that we sort of know what models we are going to use to do the adjustment. And I think surprisingly little attention has been given to issues of how to select confounders and how to select statistical models within the specific context of causal inference. There's been some work by mainly Sander Greenland, I would say, which is very interesting. So there's a bit of work by Mark van der Laan. There's a couple of people who have worked on this, but not too much, considering that all of us, I think, are facing the issue how to select confounders and how to build models within this specific context. And perhaps one reason is that we can still help ourselves with the usual traditional variable selection tools that we have readily available. However, I think that the traditional methods may not be optimal in a way in the context of causal inference, because they usually forget that the ultimate interest here is really in having a good quality estimator of the exposure effect. And so there's various issues linking to that. One issue which is very well understood amongst statisticians, I think, is that variable selection procedures, and I mean to say the traditional procedures, they might lead us to select variables that we really don't want to control for if we want to learn about the causal effect of an exposure A on an outcome Y. So in this picture, we have covariates that are simultaneously predicting exposure and outcome. You could say they're affecting exposure and outcome. And these are the ones that we really want to control for, because they confound the association between exposure and outcome. But we may not want to control for L2, even though it may be highly predictive of the outcome. We may not want to control for this if we care about the total exposure effect, because then we would basically eliminate the indirect effect here. And on top of that, it's well known within causal inference that you would basically induce spurious associations along this pathway if you would adjust for L2. And likewise, we don't want to adjust for descendants for variables L3 which are affected by the outcome, because if we do so, we would again induce some form of selection bias, a distortion along that particular pathway. This is very, very well known in causal inference, and I think also amongst statisticians, but still it's a type of problem appearing in many applied analysis, and a very prominent example is perinatal epidemiology, where there are many claims that one should adjust for birth weight since it's a strong predictor of perinatal mortality. But that may be really a bad idea if we care about, for instance, the effect of maternal smoking on perinatal mortality. Well, then birth weight is a descendant, and we may not really want to control for that. So that's one concern, and the bottom line is that if we want to do confounder selection, if we want to select covariates to adjust for in order to control for confounding, then there is no escape from using some background knowledge on the causal mechanism. And this background knowledge is typically ignored in the traditional variable selection processes. So roughly, the idea is that you don't want to adjust for descendants of exposure or outcomes, so covariates that may have been influenced by either exposure or outcome. And causal diagrams, such as the picture that I just showed, can show a lot more subtleties and give a lot more insights. But I'm actually going to ignore these issues throughout the presentation, and I'm actually going to assume that on the basis of background knowledge, we have been successful at sort of excluding these covariates that we don't want to adjust for. And so I'm going to assume that we are in this setting where we have a bunch of covariates L. So there may be many of these that we consider as simultaneously, or at least potentially, influencing both exposure and outcome at the same time. Some of them may perhaps only influence exposure, some may only influence the outcome, and some might influence both. And the question is, which of those are we going to control for in the analysis? Okay, so I'm going to focus on settings where we're dealing with a lot of covariates, or we may be dealing with some covariates where at least some are continuous, so that some form of dimension reduction is needed. Because if we wouldn't do any form of dimension reduction, we would be ending up with estimators that wouldn't be very well behaved. And so, so I'm going to assume that we want to filter out some of these covariates. One suggestion that's often made is that we also want to do that to get more precise estimators. We may want to filter out some covariates in order to get more precise estimators at the end of the day, although to some extent I think this claim may perhaps be somewhat overstated, because usually at the end of the day we kind of forget about all of the uncertainties that arise by making decisions which covariates to adjust for and which not to adjust for. And I think, you know, the precision estimates that we get at the end of the day are often a bit too optimistic. And a very nice paper in this regard is this one by Butz Jørgensen. I think this is here. Yeah. This paper I thought was very nice because it shows a setting, a practical application where you actually see that if you fit just a full model involving all available covariates, say, that the estimates that you obtain at the end of the day can actually be a lot more precise than what you obtain after a variable selection process, at least if you take into account all of the extra uncertainty created by the variable selection process. The other claim that people often make to do some form of dimension reduction is that maybe we want to have parsimonious models. And I personally do not fully agree with this, because I do think that we want to have the relation between exposure and outcome being parsimonious, because this is really what we care about, and we want to have it simple enough to be able to understand. But I think we cannot tolerate a lot of complexity in terms of how this relation looks like, as well as how this relation looks like, and especially modern causal effect estimators. Even if these relations would be modeled in a very complex way, it wouldn't be really visible to the consumer of the results at the end of the day. It doesn't really make the result more complicated. Okay, so the question is, well, I'm going to think about doing some form of variable selection, and the question is, what variables are we going to select? So there may be covariates that are simultaneously associated with exposure and outcome. There may be some only influencing outcome and some only influencing exposure. So you really want to select those that simultaneously influence exposure and outcome. These are the confounders, and if we do not control for them, well, then we end up with bias. But the question is how to select those, because the usual variable selection techniques only focus on one of the relations, but not both at the same time. And to boost precision, we might also want to select some of these auxiliary covariates, because they might reduce some of the outcome variation. If we control for them, we really don't want to adjust for these covariates, because if we do adjust for them, then we reduce, at least conditional on these covariates, we reduce the exposure variation, and we would basically lose information along the way. And that's a tricky issue, really, how to do that. So I'll reflect a bit on this, and I'll basically argue that there are drawbacks to the traditional variable selection procedures, in my opinion, because they don't sufficiently target the effect that we want to obtain or estimate. I'll sketch a procedure which is a bit more focused, and which I really don't see as the final endpoint, but only as a first step. And if time allows, and it's unlikely that this will be the case, I might talk a little bit about model misspecification. Okay, so I'm going to go through a number of sort of routine procedures that people use in this context. And the most obvious one is to use backward elimination in outcome regression models. That is, we basically fit a model for the outcome. We test which covariates are associated with the outcome, and we just use hypothesis tests to decide which covariates to include in a model. And this is what many people traditionally do in this context. One drawback of this procedure is particularly present when when some of these covariates are strongly related with the exposure. In those settings, we end up with a situation where the exposed and unexposed people can be very different in terms of their covariates. And so there's a couple of implications. One implication is that if the exposed and unexposed are very different, then it's very difficult to find an exposed and unexposed person with the same covariates, so comparable people. And if it's difficult to find those, then it means there's weak information on the exposure effect. If the data don't carry a lot of information, well, then the information must come from the modeling assumptions. And so the inference typically becomes very heavily dependent on modeling assumptions. And at the same time, the validity of the modeling assumptions becomes really difficult to check, precisely because there's not a lot of information in the data. And this is one of the reasons why people have paid a lot of attention to the development of semiparametric procedures in this context. But the other issue is if some of these covariates are strongly related with the exposure, then we're dealing with multicollinearity. And so for that reason, we may need to decide to simplify the model a bit. At least that's what people would very commonly do. So some covariates might get removed from the analysis, and if we do that, we risk to obtain biased estimators, and we may actually get effect estimates at the end of the day which are seemingly precise, but they're only precise because we've actually forgotten about these covariates strongly influencing the exposure. And one one example where this is, I think, explicitly problematic is, suppose that we want to test for an exposure effect, and so assume that the null hypothesis is true, and assume that we are dealing with covariates that are strongly predictive of the exposure. Well, then, because of multicollinearity, we may need to decide to either remove exposure from the model or the covariates. And what I was told as a student is that I should force the exposure in the analysis model, because this is what we care about. But if we do that, we would preferentially exclude covariates from the model. And so in this setting, where there's really no exposure effects, and we remove L from the model, we would still find an association just because of confounding. And so at the end of the day, you get inflated type 1 errors. So one way to deal with this is to work with propensity scores. Propensity score is the probability of being exposed given covariates, and so it's usually obtained as the fitted value from a logistic regression. And the key idea behind propensity score is that you can view it as a summary of all confounders. So even if there's like 50 confounders appearing in here, the fitted value is just one scalar number, which you can view as a summary of all confounders. And so in principle, if you adjust for the propensity score, it is sufficient to adjust for confounders. And so what I think is nice here is that we can now say, well, we're going to build a model for the propensity score, and our final analysis will always be like this. Besides the exposure, we include the propensity score in the model because this is our only guarantee that we will adjust for confounding. And even when there is an issue of multicollinearity, we just force the propensity score in there. The implication may be that you get estimates with a lot of imprecision, but maybe the imprecision is just an honest sign of how uncertain we ought to be about the exposure effects. What I think is good to notice is that since the propensity score is a model for the exposure, if we are going to build the model, we are actually going to primarily target these covariates that are predictive of the exposure. And so the kind of confounders that we would typically select may be very different from those that we would select if we build outcome regression models, where we would prioritize the strong predictors of the outcome. I think this is also an issue that has received relatively little attention. People have sort of made comparisons between regression and propensity score adjustment. But to the best of my knowledge, most, if not all of this, is looking at fixed models, settings where we a priori know which covariates to deal with. And I think the procedures might actually behave quite differently in combination with model selection. Okay, so the bottom line is that propensity score methods could have a very different behavior when you apply them in a context where we do variable selection. I think they might give, at the end of the day, a more honest reflection of how uncertain we ought to be. We might find less precise estimators, but perhaps this is just a more honest reflection. And the reason why we might find less precise estimators and find a more honest reflection is because since we're really looking at the relation between covariates and exposure, we can more easily diagnose that the exposed and unexposed people are very different. And one related issue that we have actually looked at is, and I'm only going to briefly mention this, but we've also looked at, suppose that you do some form of model selection. Suppose that we have a bunch of different propensity score models, and we use some procedure to select which one to use for the analysis. And suppose that, as we usually do, we basically forget about how we actually chose that model when calculating standard errors. Well, usually the standard errors that you then obtain are still pretty good approximations to what they ought to be if you take the whole model selection process into account. And this is much less the case if you work with outcome regression models. So this is the good news, but the bad news is that if you work with propensity score models, then you will actually prioritize strong predictors of the exposure. And so in particular, it may be that in the analysis, you would be very likely to include covariates that only predict exposure, and thereby take away some of the variation in the exposure. So we basically adjust for variables that we don't even need to control for, and by doing so, we lose efficiency along the way. So actually, what we would ideally like to do when using propensity score methods is ideally we would like to prioritize the strong predictors of the outcome. And there's been results on this saying that if you want to get efficient estimators, you really want the propensity score models not to contain the strong predictors of the exposure, but you want it to contain the strong predictors of the outcome. And this is rather tricky, considering that a propensity score model is a model for the exposure and not for the outcome. So how to do that is not entirely straightforward. And I think part of the reason is because it may even be difficult to figure out what are the strong predictors of the outcome if you consider that we are dealing with these issues of multicollinearity. Okay, so what are the alternatives? Well, we might focus on procedures that sort of look at both associations. So the previous procedures either looked for covariate outcome associations, and the propensity score methods looked at exposure covariate associations. Alternatively, we might look at both associations and basically try to find those predictors that are simultaneously associated with exposure and outcome. And I'm listing a couple of papers. This is a Biometrica paper, very recent, and this is a forthcoming discussion paper in biometrics, where they basically link exposure and outcome models through dependent priors and hope to sort of make it more likely to include strong predictors of the outcome in the model for the exposure. Okay, maybe in view of time, I'll basically skip this this bit. But basically, one concern that I have about all of the previous procedures is that they basically try to figure out what are the confounders that we want to control for, what are the covariates that we want to control for. We use hypothesis testing in one way or another. But what I feel a bit uncomfortable with is that at the end of the day, if we use the procedure, it's very difficult to understand if the covariate set that you end up with at the end of the day is somehow going to maximize the performance of the exposure effect estimator. And so, for instance, if we target common predictors of exposure and outcome, we may forget that some of these auxiliary covariates could help us to boost precision. And so there's lots of reasons why I think that there is really no guarantee that all of the previous procedures based on hypothesis testing give us necessarily a quality effect estimator. So we've been thinking a little bit how to have a more focused strategy that really sort of guarantees that at the end of the day we will get a good effect estimator. And we basically looked back into the literature and started with just change and estimate procedures. So this is the kind of procedure where people say, well, we are going to adjust for the covariates if the adjustment makes a difference, if it causes like a 10% change or more in the effect estimate. Well, what I do like about this kind of idea is that it really targets the magnitude of the effect estimator. So it sort of tries to focus on the question, does it make a difference if we do the adjustment or not? And I think this is quite nice, but what is not really nice is that it's very simplistic. It ignores the imprecision of your estimates. It may be inefficient because it's not going to select strong predictors of the outcome. And a major concern is non-collapsibility. So it may be that you would see a change in your estimates, even if there is no confounding. And this is something that could easily occur in nonlinear models, like in logistic regression models. Adding covariates could easily change your results, even if the covariate is not associated with the exposure, and so if there is no confounding. So we basically wanted to keep sort of the same idea, but get around of each of these three problems. And the way how we did this is, so the way how we dealt with the first two problems is we decided to sort of focus on mean squared error. How can we choose the covariates that we want to control for such that it's going to minimize the mean squared error of the estimator? And second, in order to deal with this non-collapsibility, we decided to focus on standardized exposure effects. And I'll give you an impression in a minute. Okay, so the idea is that we are going to adjust for those covariates that sort of are going to minimize the mean squared error of the estimator. And this is not a new idea. It was the key idea in this JASA discussion paper, which talks about focused model selection procedures. For instance, being applied in the context of logistic regression, where people try to figure out what covariates do we need to control for in order to minimize the mean squared error of the exposure effect. A potential problem with these procedures as they were originally proposed is that the meaning of this coefficient is really changing depending on what covariates you control for. This is because of this non-collapsibility. And so we try to get rid of this by focusing on marginal or standardized exposure effects For instance, we could use the model to predict what would happen if everyone was exposed. So I'm setting the exposure to 1 for everyone, and we can average this over all covariates. And then I'm going to predict for exactly the same people what will happen if no one was exposed. So I'm setting the exposure to 0, predicting what would happen, and then again averaging. Okay, I'll not say too much, but I'll give you an impression how this was working in a famous right heart catheterization study, where we looked at the effect of the catheterization on 180-day mortality. It's a pretty large data set, and we were dealing with 61 covariates, sort of telling us something about patients' health condition mostly, that we could control for. So the idea is that we're going to question which of these 61 covariates do we need to control for in order to get a good effect estimate. We're going to use the mean squared error as a sort of focus. We'll try to minimize mean squared error. Of course, calculating mean squared error is not particularly easy because the mean squared error involves a true effect size, which obviously we don't know. So what we did is we used the asymptotic theory in Vansteelandt and Hjort to sort of get approximations for how the mean squared error ought to be, and at least up to a constant. So I'm not going through this in view of time, but at least up to a constant, we can calculate what the mean squared error would be asymptotically. And Brookhart and van der Laan use basically a similar idea, but using cross-validation, which we try to avoid because it's computationally intensive. So this is how the results would look like. So you can see different orbits, and an orbit refers to a model with a particular number of covariates. So orbit 10 refers to a model that adjusts for 10 out of these 61 covariates. Which 10 could be different? So there's different models within that same orbit. And so we did a stochastic search through all of these models. Well, not all of them, but many of them. Each time calculating what the mean squared error of the exposure effect would be. And so the best result is what you get to see on the y-axis. And so you can see that low mean squared error is obtained already for models that only control for just a couple of covariates. And in fact, the lowest mean squared error was for models with 2 covariates only. This picture is one that we adapted from a biometrica paper by Caniciano on confounder selection, which I quite like because what it shows is basically the result. So the result was expressed as an odds ratio. So bigger than 1 meaning that there is a harmful effect. So first you can see what happens in a naive analysis, which does not control for covariates. And then as soon as we adjust, you can see that the marginal odds ratio goes up to a little bit over 1.3. But in fact, what you can see on the picture is that we get very stable results. Whether we pick a model with 2 covariates or 20 or 40 doesn't really seem to change the magnitude of the result very much. If you would focus on conditional odds ratios, so what you would usually obtain from a traditional regression analysis, logistic regression, well then you get somewhat different results, which is due to this non-collapsibility. And they're just a little bit more sensitive, I guess, to what orbit you are really in. So these are basically the kind of results that we obtained. So fitting a full model with all 61 covariates would give us this estimate with a confidence interval. This is what we obtained with the model that gave us the lowest mean squared error. This is what we found with a standard backward elimination strategy. So you can see that the interval is a bit more tight than compared to the full model. Although personally, in this application, I might feel more comfortable actually to report the full model analysis, because what this confidence interval does not take into account is the additional uncertainty created by doing that model selection process. And this is, you know, a topic of further research, how to deal with that. Sure. Yes. The black ones. Yeah, the black ones are always the marginal loss ratio estimates.
And the conditional ones are red.
Exactly.
And
Yep.
the width of the bar is the confidence interval.
For the marginal, yes. Yeah. Yeah. Sorry. Yeah. And so the vertical line is just using the full model as a reference for comparison. Okay. Well, let me summarize this a bit. So, what I basically try to argue is that I think it's nice if the model selection procedure is kind of targeted towards the exposure effect that we want to have at the end of the day. And I don't think the traditional variable selection procedures are really focusing on this. So I think that to some extent may call for new procedures on how to select confounders, taking into account that confounders are simultaneously associated with exposure and outcome, and that we may be dealing with issues of multicollinearity, as a result of which we may have a tendency to sort of get rid of or discard strong predictors of the exposure, even if they are confounders. Personally, I feel a bit of tension, and you may have noticed it throughout the talk, tension between focusing on precise estimators that are close to the truth in the sense that they have a small mean squared error, versus targeting estimators that give an honest expression of how uncertain we ought to be. For instance, that could be we want to target confidence intervals that have the right coverage. I think there's a bit of tension between that, and I think the propensity score methods focus more perhaps on giving an honest expression of the uncertainty. But that may come with a price of being less efficient, so they may be a bit less close to the truth, perhaps. What we call focused confounder selection, so the kind of strategy that I showed in the application, was targeting minimal mean squared error, but it doesn't really give a guarantee that the uncertainty estimates associated with it, like the confidence intervals, will have the right coverage. And this is on the one hand because if you focus on mean squared error, then we tolerate some bias, except in large samples where the variance would disappear and bias would remain. And also we ignore model selection uncertainty. We ignore all of the uncertainty created by going through that variable selection process. Perhaps with the exception that I briefly mentioned before, when I said if we select between different propensity score models, it turns out, as asymptotic calculations show, it turns out that the standard errors that you obtain are pretty good, even if they ignore that model selection uncertainty. So I'm a little bit myself in doubt, whether we should target small mean squared error or have a good coverage assessment. And personally, I worry much about bias, and I might be a bit more tempted to give more emphasis on reducing bias rather than mean squared error. I'm not sure if I... Okay, this is my last slide that I'm going to go over. So I just want to mention an idea that I quite like, proposed by Sandro Greenland. He says, well, if we have a bunch of covariates that we have collected, then very often people had good reasons to collect those covariates, and so it's very likely that all of these covariates will be at least somewhat related to the outcome and at least somewhat related to the exposure. So he says, well, probably all covariates that we have available are to some extent confounders, and maybe we actually want to adjust for all of them and not do any selection at all. Of course, the information may be insufficient to just put them all in the analysis, but maybe we can use some regularization approach, and he uses ideas like rich regression in that particular context. and you know the Bayesian analogs. So and I actually quite like this idea. It has its own limitations because you know if you want to control for many covariates, life may get more complicated when there's missing data in some of these covariates and measurement error in others and so forth. But I kind of like the idea of not doing any selection at all. Partly I like the idea because I think uncertainty estimates, correct confidence intervals will be much easier to obtain if we use that kind of procedures and if we go through some very complicated variable selection process and have no clue how to incorporate the additional uncertainty at the end of the day. A disadvantage, I think, is that the regularization approaches like ridge regressions are not really having in mind that at the end of the day we only care about this exposure effect. So perhaps there is potential for targeting these approaches more towards the quality of the exposure effects. And perhaps one way to do that would be to sort of try and estimate the covariate effects by minimizing that asymptotic mean squared error that are used as a focus previously in the model selection or confounder selection process. But I'm going to stop it here. Thank you very much.
Can we take any questions in the few minutes we have? Sure. Yeah.
In practice, it's usually the propensity score model is fitted on the entire data set, just as the one on which the final analysis is based.
Can you seem to be just louder for print the back? I'm not sure. Just repeat the last question. I'm not sure I get it.
So I was curious whether people typically pick the propensity score, the weightings in it on independent data, and if they don't, whether in the final model the association is exaggerated between propensity score and exposure.
Are you thinking about like the settings where we do prediction and sort of evaluate the quality of predictions on the same data as we build the model? Because I don't think it's as much an issue with propensity score. It's not that we sort of try to make a prediction. So propensity scores could enter as a covariate or they could enter as a weight, which of course introduces some imprecision in the analysis. But so long as we correct for it, I think through the standard error calculation, I think we should be pretty fine. Yeah.
I might have just missed this in your example. Did you, when you do the problem, was that an adjustment based on the propensity score?
No, sorry, I was a bit unclear about this. No, this was doing a traditional regression.
Can you do the same thing?
We could do the same thing, yeah. With
Would that be an advantage in one of the?
yeah, so we've actually started to try and work out the analog for propensity score adjustment, but we're not really completely there, to be honest. And it's not that I think the differences might not be particularly large, but since we focus on mean squared error, I think also in the propensity score we'll sort of try to maybe primarily put those covariates that would sort of reduce variance. I'm not entirely sure what to expect, but I don't think we will sort of retain the kind of properties that I suggested before for propensity scores, that they might give a more honest reflection of uncertainty. I think as soon as you focus on mean squared error and tolerate bias, that we may no longer have this. But I'm not entirely sure what to expect. But in principle, technically, we can do that mean squared error calculation.
A few more questions? You were gonna...
So I just wanted to raise the obvious caveat to all this sort of work is that there's an underlying assumption that you have all the confounders that might exist, and in particular, often in, for example, etiological studies, you don't, or you don't believe you do. So, you know, you're never really getting towards the correct. And a particular example of that is, of course, when confounders will have measurement error, and you only have the measured value of the confound, you don't have, if you like, the underlying value of the confound. And none of these methods will, of course, get over that kind of problem.
No, I fully agree. It's no, they don't. Unless you would, you know, I guess all you can do is look at sensitivity analysis in addition, or use instrumental variables approaches to as an alternative. And one particular concern, maybe that I want to raise, is that if there is, like this picture is showing a setting where there is potentially unmeasured factors confounding the relation between exposure and outcome. So this, you know, in this setting, the analysis would end up with bias. And one concern that has been recently suggested that I skipped over is that the amount of bias that you will end up with basically gets inflated by the variance inflation factor of A, which can be quite substantial, and L is a strong predictor. So that's another reason why we really have to think, how can we screen out or filter out strong predictors of the exposure that are not related with the outcome, because they could amplify all of these biases.
One last question.
Yeah. Yeah. I do think that you could say, in addition to, I'm going to use a propensity score to control for confounding, but in addition, I'm going to allow for interactions between exposure and some of the covariates that I find particularly interesting. For instance, regression adjustment for the propensity score would allow for the inclusion of covariates besides the propensity score. And also some of these methods that use propensity score as an inverse probability weight have the capacity to include covariates alongside with the exposure. I do think it's a very valid and good point. But I also think that there is a potential, even when using propensity scores, to still look at interactions with meaningful covariates.